And ta-da! Hello! Who's here tonight? Getting started. If I'm honest, okay, question one. Looks like my audio is loud enough. My face is blurry and I haven't even started drinking. Okay. But here we are. So starting out tonight, I know there's some people here. I am going to be starting tonight with something called Fresh. Can I zoom in on that? Do, 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 do. And this is a strawberry kiwi. It's like a bubbly, but there's cannabis in it. So this will be really exciting and delicious. Available at the local shop. And I feel like after reading this week's chapters, that they are not actually the most compelling chapters that we're going to face, but I think I almost wonder, like, there are, anyways, we'll get to it and we'll see what you think on this sort of on the topic. And I use Tostitos glasses because they have this nice, wonderful, wide mouth. And anyways, so let's see. So we are going to. What are we going to do? Okay, so we're going to switch to desktop sharing mode because I did. What am I doing? So this week's topic. So last week was solid principles, one of two, where we covered the S and the O in solid, which is single responsibility and the open close principle. This week we are doing the L, I, and D and their impacts on our decisions around architecture. So how do we do? I think that these are not the most compelling, except for D. So the dependency inversion is really quite compelling. It is the most, it's actually described by the author as the most visible thing you can do in terms of designing an architecture. I suspect that it is also one of the more complicated things you can do because it seems to add incredible amounts of complexity. Actually, it all seems to add complexity in terms of developing here and now. And so architecture seems to be about increasing the effort in advance so that, at least so far, I mean, we're 10 chapters out of 30. So far, architecture or system design seems to be front loading a lot of complexity in terms of our application design so that when our project scales over time in terms of number of developers who have to work on the project with us, or the speed at which we have to do things, or maybe the database that we're connected to has to be changed because I was talking to some here. So as an aside, and you can actually look at the Max Gerlach interview that I have up on my channel, and I was talking to Max, and he's working on an AI product with a MongoDB backing it. And Mongo is supposed to stand for humongous, and as such, one would expect it to allow you to build very incredibly, mind-blowingly huge databases that shard and scale and blah, 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 blah. Well, it turns out, at least from this one developer's experience, Mongo seems to have, I think he said it was a 4 terabyte limit before it starts getting screwy. So if you look at the exercise around architecture, and we're going to talk about this later when we get into the pages. Maybe I should do more of this just solo cam. I don't want that distracting us. Anyways, so if we're talking about this situation where we've got this website, or we've got our application services running, we have found ourselves in the enviable position of scaling up past the limits of our current existing database, a MongoDB, which I guess runs into the 4 terabytes according to Max, who I was speaking to. So if we had, and here's the other thing, he works at a unicorn. It's this company that has an over $1 billion valuation. So all things considered, really enviable place to be in, but you're reaching the absolute limits of what your data background could do. And so architecture in the way this is described, according to the or at least my read on it so far, seems to be architecture and design around these solid principles is about front-loading complexity. If they had front-loaded complexity such that there was a boundary line, and we're going to talk about boundary lines in a couple of weeks, but if there was a line dividing data persistence from core application, the cost of switching to a different database model or engine, it's a database engine, would be the cost of writing the one thing on the other side of that interface. And we'll talk about that maybe a little more. So I can go off of solo cam and we'll go to desktop cam. That's not it. This one's desktop cam. And we will go to today's notes. Again, not the most compelling week on the L and the I, but we're going to go through it anyways. So this one, so the Liskov substitution principle is, or substitution principle with an L for the, so that it fits within SOLID. It's at its core, it's about setting a base rule for how inheritance works on your objects. And every subtype should be able to be used by in the same place that its parent. So if something inherits, it should have, if something inherits from a parent class, it should be completely substitutable with the parent class, no matter how far down the chain you go. So what you should not be doing, anyways, and if we look at this first image from the book, and I've recreated this, I know that one week we had somebody, when we went through all of these system design interviews, people were saying, what is this flowchart tool that they're using? And this one is called Whimsical. I finally found it, and it is so easy to create flowcharts with. So we could, if people were here chatting, we could talk about that for a bit. But let's just barrel on through. So what we're looking at here, and this gear represents an interface. And to remind you what an interface is effectively an object in your code that has no, it's just a list of the functions that you could use that specifies, we say that it specifies a contract. So if something implements an interface, it must have all of the functions from within that interface. This is a really key point, but the interface itself doesn't have any code. It's like a placeholder object. Now, if something implements an interface, the business license or the personal license, they implement the license interface, well, then according to substitution, the billing controller can use either of those types of objects. And in this case, what we're looking at is a situation where perhaps business clients will purchase numerous seats, and maybe their calculation for fees is much higher. Maybe a personal license is a single-use lifetime license, whereas business licenses work on a monthly recurring basis or something. It doesn't matter what these do. The point is, in terms of your billing, you by allowing you to substitute in any type of license or substitute any type of object, the concrete code that executes what's going on can be easily swapped in and out over time. And that's fine and so this is my analysis of this part of the book so far, is that's fine, sure, that's good, but I don't know if it's so compelling that I guess it's valuable to say it, but it isn't super compelling as an argument goes. Now, here's another example of a violation of the Liskov substitution principle, where, and this is said to be infamous. This is sort of the global recognized example of a violation of the LSP, Liskov substitution principle. So if I've got a controller that is a drawbox controller, and it can take a rectangle which has a set height function and a set width function, and arguably you would have your get width and get height, and so you could pass your rectangle to a drawbox. But if you have a square object that is inheriting from rectangle, and you try and use it, and you have designed your square to say set side, well, this thing that is a child, a rectangle is a superset of a square, right? Because a square is just a rectangle with equal sides. Now, you couldn't pass a square to your drawbox function. And that's the example of the LSP, why it's a problem to violate. Honestly, and again, in the book, the example provided was really long and convoluted. I thought a little bit annoying, and I'm not going to go into it because it was just terrible. But the conclusion is fine. And the conclusion is that if you violate the substitutability, you're going to have a bad time, long time. Oh, Sir Croc! I always see this example in the kids don't use inheritance. Right. So, fair, but the fact of the matter is that if you had a square object with a set height and a set width, then you could use it and in the drawbox controller, and that's the point of the LSP. The point of the Liskov substitution principle is that every child, everything that inherits from the boss object should be able to be used in any function that also uses that object, and that's the thing. Now, the interface segregation principle, my notes are probably not very great here. I clearly should have given a reminder. Now, last week we actually talked about what this is, and so we're just going to get this illustration as well. The interface segregation principle says don't depend on anything that you don't use. And by not depending on things you don't use, you're not going to have problems long term. I have some good examples, I believe, of this one, so we'll talk about it in a second. So if I had a function, or if I had a class that executed numerous different types of functions, so my user number one, for example, uses this class to execute operation number one. My user number two uses this class to execute operation number two, but doesn't need number one or number three, and so on. In theory, I would have expected Uncle Bob to have already suggested that we split this operations class into a series of classes so that we fully segregate these things in terms of the single responsibility principle. But in the event that what we've done is we've taken a facade, right? Because we've talked in the previous week about how sometimes we might set up a facade class. So maybe this is an operations class that loads up all of the other classes to make it a single unified place to make these sorts of calls. Anyways, so the way to properly segregate your using the interface segregation principle is have your operations controller publish multiple user interfaces. And as such, user one only depends on operation one being there. And it takes a little bit of abstract thinking to get to this point and to really let this sink in. But if you think about it, user one, operation one, you could move that out into another application entirely and not run into problems, because it's as opposed. And if we scroll back up to this one, if I wanted to move user one out into a standalone application, say I've got my desktop app, I've got my Android app, I've got my iOS app, and each of them has a different set of things they have to do. If I wanted to take this and I move user one onto an Android app, I actually have to bring all of the code of operation 2 and operation 3 along with me. And we'll get to an example. There's a really good concrete example of this out in the wild that we'll talk about in a second. Now, in this version, where we have written interfaces for each of these operations, we can actually move out the user one op, and we can do this without incurring as much overhead. And so in general, there's a typo there, but that's okay. In general, the theory is that it's considered harmful to depend on things that you don't want to, that you don't need. Now, and the greatest example of this comes from this Windows Nano server example, and we're going to talk about it in a second. So, and in development time, it can cause unnecessarily recompilations if you're working locally, or redeployments if you're not. So again, imagine that Android example from above, where I had to move everything from user 2 and user 3 along with everything from user 1. Well, in this case, because I've moved it all, what if I discover a massive security flaw in operation 3? Well, in that case, I've got to redeploy the operation, or redeploy the application on Android. And so the expense that comes from depending on something that I didn't need is this massive it can turn into a massive overhead. Whereas if I had just separated off the iUser 1 and Operation 1, just that, and there's a security flaw in Operation 3, nobody cares, right? So that's the point there. And so we want to talk now about another great real world example of this was the Windows Nano server. For those that don't know what Windows Nano server is, it came out, looks okay. So it was, when I first read this, it was probably about 5 years ago. And it's effectively containers. We all know about what containers are nowadays. I think we should. I mean, Docker is an example of working with containers, and Windows Server rewrote their entire container philosophy or around the theory that you start with the minimal zero package thing that it is required to boot up an operating system. So, and then everything you want to add to your server is another thing. So is a package that you install on your own. So let's take a second to look at this picture of the old way. So in the old days, 2003, when dinosaurs roamed the earth, I rode a triceratop to school. Actually, that's not true. I was already working in 2003. Anyways, so in 2003 and before, Windows NT, Windows 98, what was Windows NT was, anyways, not important. I think that was 95 or 94. Anyways, not super important. But what you would do if you wanted to run Windows on a server in the early 2000s, you would take your Windows DVD and you would slap it in the DVD drive and you would install the entirety of Windows NT. And so what that gave you was ASP2, yeah, hey Slater USA, ASP 2.0. I was writing Visual Basic for applications. So at this time, I was writing things where you click a button in Excel and it just goes boop, 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 and populates all of the cells and uploads. Anyways, it was really cool. Put the entire site in a form tag. Perfect. Anyway, so it's good to have other old folks around who also wrote a dinosaur to work back in these days. So you would have, with Windows NT, with your Windows install, you would have everything. You'd get your email client, you'd get Active Directory, you would get Minesweeper, right? You would just get everything, and that was the option that you had. So the problem is, if you are running a server in production out in the wild, and there is a massive, hey Amadeo, there is a massive problem if you've got to incur application downtime if Minesweeper has a critical security bug, right? So Nano flips that on its head, and it says server core, and this is an example. Server core, if you want to run a minimal interface, you just get the kernel, and that's it. And that is the most secure level that you can have. Then you would say, well, do I need this server to be an email server? Well, if yes, then you install the email package on top of that. And if yes, you also need to do Active Directory. You install Active Directory. But if you don't need Minesweeper, or if you don't need a GUI shell interface, you don't install them. And so Windows Nano Server is really a great example of this interface segregation principle, because you are not. I was in a front end dev job interview circa 2012 where a guy said his entire lung capacity, that ASP entire site wrapped in, was totally cool and good. Well, I, I don't know that I agree with this person, but you know, there we go. So, anyway, so we're saying back over here, we're saying, well, what happens if instead of, so in terms of interface segregation, well, what happens? Your Nano server, where you just have the kernel, has way faster startup time, right? You have to open way fewer ports, so it's more secure by default. VHD size, that. Oh, virtual hard drive size in gigabytes. So the size of the minimal install that you need is significantly less. If you look at the frequency that you have to reboot the server through, for example, a security patch or something, far lower, because you don't have as many packages installed. And your critical patches, again, if Minesweeper has a massive security flaw in this Nano server instance, you don't have to worry about it because it was never installed on your machine to begin with. So it is security by not including shit in your application. So bring that back to, he was very persuasive, and later on I was glad that I didn't get the job. Well, yeah. So from a security perspective, and we're talking about the interface segregation principle, what is this? Content of the, yes, that's what I'm doing right now, and I am talking about it. And so the conclusion of this interface segregation principle is that if something carries baggage that you don't need, it can cause you troubles. And so I think this Windows Nano server example, so we've got this is the idea, right? You've got your kernel, you install just the packages you need, and your payoff is, because the image is smaller, because there are fewer things that you have to start up, because there are fewer ports open, it's more secure, because you have fewer patches to install, you have fewer reboots you need to do. All of this across the board is, back again, interface segregation. In a concrete example, it's not quite, well, I guess this is discussing the architecture of Windows servers. So there you go. Now, dependency inversion principle. This one is super visible, super exciting, super useful. This one is standalone in being like ridiculously important in terms of our, well, in terms of it just keeps coming up again and again. Invert your dependencies. So the most flexible, and these are quotes right out of the book, by the way, these initial bullet points here. So the most flexible systems are those where source code dependencies only refer to abstractions. And we kind of talked about that up here. This is more robust because by breaking things out into our interfaces, we are more flexible over time. We can now. So he also says, never depend on concrete classes. Instead, always write an additional interface layer when you're consuming something, like when it is a third-party product, when it is even within your own systems. And we're going to talk about this next week and the next 3 weeks, I believe, we talk about components. If you are designing a component, write interfaces so that one segment of your code can be decoupled from the other segment of your code. So don't depend on classes directly, pass them in as depend on them as interfaces and pass the concretions in as code. So good software designers work hard to reduce the volatility of the interfaces. So this is, I mean, if you're lucky, I think. So this comes from the book. So the theory is that an interface does not have to change nearly as often as a concrete class, and the concrete class or the interface doesn't care about any of the private methods. You can do all sorts of things that are not in the interface in your class as long as it has at a minimum the functions that are specified within the interface. So that's important to make note of. Now, so this is the example that I come up with, and I use this one time and again. We say, if you are calling a database's save method directly, instead of calling a database's save method directly, if you call it through an interface, you can later swap out the database by editing just the one file that makes the calls to the concrete classes. And anyways, so the interfaces are key to stable software architectures. Stable software. Yes, we had plenty of discussions at work talking about designing the layers in order to remove dependencies to specific libraries and coupling your implementation. Right, exactly. So Amadeo works with me, and how did because we're discussing this at work, but we're a couple of weeks ahead right now. So how did today's chat go? I haven't had a chance to follow up on C. I did stop it. I don't know if you were there, so I wanted to make sure I logged in or it was running properly, and so I had to log in for a second to make sure that somebody was hosting this week's discussion. And my 2-year-old had just done a poop in the little potty because we're doing potty training, and he started screaming at me, and we were all very excited. Oh, okay. Well, you're here now. That's good. And I also missed it, and we had big potty training fun today. It was really, we're having a really good time, but my 2-year-old might murder me by the end of this week. So anyways, back to this. Stable software architectures are those that avoid depending on volatile concretions. And so this is exactly what Amadeo is talking about right here too. We talk about writing interfaces to separate the things that we are including from the things that we're writing ourselves. And that allows us to swap out third-party stuff. Now, this is a summary of the rules that are key to. Okay, he published these. These are the rules, and then who's that? Hey, John, good to see you again. This was the stuff that you were looking forward to, the solid principles stuff. So a summary of the dependency inversion principle rules is: don't refer to concrete classes, don't derive from volatile concrete classes, and it's fine to derive from an interface that has all of the functions in it. But deriving directly from the class means you are tightly coupled. If you are If you have an interface in between, you're more loosely coupled because you can swap out anything at a later date. Never mention the name of anything concrete and volatile, and so on. So the key to this dependency inversion principle is to ensure that all dependencies point in one direction across the boundary line. So this is an example of doing it the wrong way, this first one. So the application calls your specific function, your specific library. You have a service factory that calls your specific library. And if you want to swap anything out at a later date, it's really challenging to do that. This is so what you have to, I have to zoom this out a touch. Oh, John, this is something called whimsical. You were the one who was asking, weren't you? You were saying, what is that flowchart making? Whimsical. Dun, dun, dun. It's awesome. It's so good. So here it is. So here you go. So if I want to make a new thing, we go like this. It is super simple. And so it is missing some features that I think would be nice to have, but other than missing a few features, it's just so quick to put together your flowcharts and things. So this is the one that they are using in those exponent interviews. Exponent. Anyways, uses whimsical. So it's sort of like a really low rent version of your... I wonder if they do stuff that does proper UML. This is flowchart, wireframe. Anyways, not the point of today, but I know that John in a previous week was asking where we found the whimsical. So there we go. So compare this one where we're working directly to this one where we have decided on an arbitrary boundary line, right? This is, boundaries aren't real. We make them up. We make these decisions as the architects of our system to say we want to separate concrete stuff from our core application. Now, important to note that our core application has a part of it that references the actual, concretions. So the specific name of the specific database that you use gets loaded within a single file in the application. But these are decisions that we make. As architects, we say everything that is concrete lives on one side of the boundary, and our application will load it by name and pull it in with permission in one place. But in order to have this work as expected or intended or as needed, we have to write additional code called interfaces that are effectively standalone files that say, in the service factory implementation, right? So my service factory interface needs one function, and that's the only thing it needs. Now, in the real world, my service factory can have dozens and dozens of functions. Doesn't matter, as long as it has the one that I say it needs to have because of my interface. And that's how our interfaces stay more stable over time, because we don't care what other things change. We don't care what goes wrong anywhere else in that package. As long as it still has our make service function, then we're happy. So and then the service up on the side over here has, again, it it will just have the functions that our service calls from the concrete service. And that's just just the thing. Just the thing. That's just what happens. Discuss why the second version is better. Because we can separate those things out and change them and swap them at any given time. Most systems, and I did just say that, most systems will have one concrete component, and that would be our application. But the interesting thing about that setup or that condition is we can have multiple applications. Like, one application could be your unit tests as opposed to the thing that launches your website or your desktop app, or one could be a mobile phone or application. One can be an iOS or an Android. So, and those would tell you the name of the thing that goes into your factory. So the conclusion of his work on the solid principles are that it's first of all that the dependency in inversion principle shows up again and again and again in different forms at different scales. So we see it again at the component level. We see it again at the architecture level. We see it at this sort of starter level, and if you went back all the way down to clean code, you actually see solid principles down on the clean code level as well. This is the most visible organizing principle, and the reason that it's the most visible is because you have to write all of these additional interfaces to what? To create a way to separate your code and draw these boundaries. So in writing the interfaces, you are creating the boundary. So then dependencies, this one is so important as part of all of this. The dependencies should cross the boundary lines in one direction only. So all of your concrete stuff depends into the application, but the application doesn't need to know about anything outside of it. The only place where that gets violated, again, is within a single file inside your application, in where the specific names are listed, or sometimes those are even configurable. But that's the dependency rule. This is the image you want to keep in mind. Make sure that everything depends in a single direction. So that's this week's content in terms. Oh, I've updated that. These things now have names. Okay, so that's the end of solid. Next week, and if I'm honest, I thought the L.I.D portion was a little less exciting than some of the earlier stuff. I don't think the substitution principle was incredibly compelling. I thought the interface segregation principle was really, actually, that one was really good. That was really good. And obviously dependency inversion is really important and makes a lot of sense. And it is the most work. It is the most additional work to do. So one would hope that it keeps itself valuable over time. In my personal experience working with this, it never dependency inversion principle is the most work, in my opinion, I think, because you have to write so many additional interfaces to do it correctly that that's what I think about it. Is there are so many more files you have to worry about. not a crazy number. Like if we were talking about writing in C or Objective-C, I was doing this on, you have to have a header file anyways, and an interface is effectively just like a header file, right? So it isn't that much more, but it does, when you are early stages of development, especially in the 2 or 3 developer shop, or it's a small one-man show, writing an interface to communicate with a thing that you're just going to use anyways seems like so much extra work. But the point of this, the point of Solid in general, is we are front loading the cost of additional development work in order to make it scalable when the team grows to 10, 20, 30, hundreds of people, and when you go from being a small startup to a scale up to a, profit machine, right? So, anyways. So in terms of the next weeks, in the next couple of weeks, we have component principles for three weeks on component principles, and then in 4 weeks we finally tuck into what is architecture properly. So there you go. I'm fleshing out what these plans actually mean, or what they actually talk about here, but that's it. That's this week's. So I don't know. Oh, that's week 5. This is this week. So there are close tabs to the left. Wrong one. I wanted close tabs to the right. So that's it. That's the week. And what are your thoughts on this for those of you that are still watching? I'd love to know so far what you think of the content. Have you read his book? Am I reading it right, in your opinion? Are you finding things that we're talking about useful in terms of changing the way that you look at how you program? Because I definitely am. I've seen things in reading this about mistakes that I made in the past that I would do in a different way going forward. I've also, in terms of that Windows Nano architecture discussion that we had a moment ago, yeah, mixed feelings about Uncle Bob in general and object-oriented as a paradigm. But you spent a lot of years in Java, didn't you, John? And so you've not got Stockholm syndrome from object-oriented? Or anyways, so as I was saying, I wish there were a little more talk about the trade-offs and the downsides. Too much abstraction, too many, So I guess that might answer one of the things. I saw one of the C# developers or architects had a strong anti-interface position a few months back on Twitter, and I was wondering where that was coming from. But maybe more people do say that there are too many interfaces. And then I hate when I'm debugging, trying to trace through code flow, and I hit an interface or some listeners, and I can't figure out where the actual next concrete class is, who's listening, who actually implemented that interface. Right. And so that's where, and does Java not have what do we call it, like a global main startup program that kicks off configuration and kicks off dependency injection and sort of, because in C sharp, there's a single place to go and look at the list of concretions. Yeah, okay. So, but I assume it's also when you do things that are super fancy, it is kind of possible. And when projects get big enough, it's really hard to find the associated concretion with an interface. Yeah. So, anyways, I absolutely think I'm going to do some things differently having read this far, or recommend some things differently. So, I guess if I hit some abstract interface and then I have to track down some XML file where the yes. Yeah. Right. It's but is I, I mean we have Bob's experience, right? So Bob's had his 60 years, and so yeah, instead of F10 to step into this method, right? So yeah, I've been there too. Just follow it down until you get to the point where you're looking for, yeah, you're looking for the where am I? What am I actually in? Although I guess that also comes in a stack trace if you can get it to throw somewhere, you would see that it goes through this specific library. So, anyways, anyways, the point is he is super hot on interfaces, the dependency inversion principle by moving things. I feel like that one direction thing is really, I feel like those orange lines I find to be super compelling. I think going in one direction makes a lot of sense. And I and from a previous week, what was it? It was the so in week 3 we see this one where all of the interfaces go in towards the business rules, where they converge in that one sort of spot, which that felt really compelling to me. So, anyways, that's the week. I don't want to take too much of your time, but I think we got through L.I.D, and next week is components and how do we work with them. Super excited for it, and thank you for coming by, and we'll talk to you soon. And then we stop recording.